Hi there. Welcome to another video lecture with Math 348. I'm going to do an example for you, which is Hermite's equation. And this is sort of to cover missing class on Monday. And so we've done some other things in class. This is just one straightforward example. And I'm going to share my screen now and talk you through it. And I'll see you back here at the end, or maybe I'll stop if I want to make some comments or something like that. So here we go. All right, here is Hermite's example. And it is a second order linear differential equation with a variable coefficient. I'm going to look for a power series solution. And so I've written down, as you can see here, here's the form of my power series, and I have taken first and second derivatives here. Check those out. And now I just want to simply plug everything into my original differential equation right up here. Pay attention to the fact that I have a for all x here. So if you think about that for just a minute, remember we had a theorem in class where anywhere that our P of X or Q of X and our G of X in our general form for our second order equations, anywhere that we had power series representations of those variable coefficients, we were safe to write down a power series expansion for our solution. Let's go back and take a look at the coefficients for this equation. They're nice, they're just polynomials. That means there's no restriction. We have a power series everywhere for this solution. Okay, so we see here, this is the P of X, this is the Q of X, this is the G of X. Nice, no worries for any kind of interval of convergence for this power series. It should be a series that converges everywhere. So now let's take our first and second derivatives. Let's plug everything into our ODE. And remember, just like we talked about in class, I'm going to do these one at a time here. So here's my second derivative. Here is the term with the first derivative multiplied by a minus 2x. And here's the 2y. And I have, as I've simplified a little bit over here on the right side of these equations, you can see I've multiplied by my minus 2x inside there. And there wasn't much to do with either one of these others. But now remember, I'm going to add all of these. Now, when I add all these up, they should sum to 0. That is what my original ODE told me. So when I add them all up and I sum to 0 here, I notice that, well, here I'm starting at m equals 0. Here I'm starting at m equals 1. Here at m equals 0. And now pay attention a little bit to the fact that when I do this, I need to start thinking about where's the term that starts with all the series. Well, in this case, it's m equals 1, right? All right, so we start with m equals 1, and then I have a couple of extras. So those extras come from, well, they come from this first term here, this second derivative, where I've got a 2a1. That's this guy right here. And then I've got a 2a0 that comes from this term right here. Okay, so both of those come out of having an extra term for m equals 0. And then I've written down each of the m equals 1 terms that you can see right here, just so that we're really clear on what all those things look like. And now I add them all up, right? So I have some constant terms here that I add up that come from here. And then I have my full series that starts at m equals 1. And now just treat these individually. So remember, we're setting everything equal to 0. So this whole thing on the right-hand side has to equal 0. That means each of the individual terms in the series equals 0. That means I set the constant equals 0, and then I set each individual term over here equal to 0. And now that second spot's where I'm going to get my recurrence relation. So let's scroll up a bit here. All right, so I deal with this term first. That's pretty easy. A2 is just minus A0. And now with my recurrence relation, I want to solve for the AM plus 2. That's the term that's further out in the series. And so everything else goes on the right-hand side, and I have a nice little form for m greater than or equal to 1, and that comes out of the fact that my series up here started at m equals 1. Okay, now I need to unpack all this. What does this mean exactly? Well, what does it mean? It means I need to think about having a couple of arbitrary constants because the A2 is dependent on A0, as you see on the left here. And then on the right, I can see that if I specify an A1, so I make that an arbitrary constant, then I get a 3 and I get a 5 and so forth. So that's going to be the pattern. So A0 and A1 are going to be arbitrary. And now let's see what happens as we follow through all of these terms. I see that A2 is minus A0. All right, so I have A0 and then I have A2. Let's use our recurrence relation here then to go from A2 to A4, and then from A4 to A6, and so forth. And that's what you see happening right here. So I start with the fact that A4, well, what is that? That's really the case where I'm looking at A4 in terms of A2. That is the m equals 2 case of my recurrence relation. So let me clean up some of the mess here. Let me put a nice box around my recurrence relation here. And now when I do that, what that's going to tell me is how to approach all of these down here. All right, so I can get A4 in terms of A2. And then once I get here to A2, I can go back and say, well, A2 is minus A0. And so then once I have that, I can go to A6 in terms of A4. And I plug and chug through those details. And I have A4 in terms of A0. So I go back, I plug through that, and I see this term popping out. And hopefully you can see this pattern starting to form. And I kind of had to look at a bunch of these before I could see it. But once I looked at A8, A10, I wanted to make sure that I had the numbers kind of down. And so everything is in terms of A0. And what I want to call your attention to is here I'm looking at A8. And look what happens. I have 7 and 4. Here I'm at A10. Well, I have the 9 and the 5. And then at 12, well, I'm at 11 and 6. So let's see if we can figure out how that's related. If you can think about this as A8, that's A2 times 4. A10 is 2 times 5. A12 is 2 times 6. So now you start thinking about what the K is and what this 2K minus 1 term is. So it takes a little while to see the pattern, but I've got all these even terms, and this is how the terms are related to A0. And you just have to play with that pattern for a while before you figure it out. But this is all my even terms. And now I want to do a similar thing with my odd terms. And remember, my A1 was actually arbitrary. So A1, it's just what it is. And then I go back up here to my recurrence relation. And all right, so I'm up here at my recurrence relation again, and I start with A1, and then I determine A3. Let me scroll up a little bit. And A3, look how that turns out. So it is the case here that when I'm starting with A1 in my recurrence relation here, right? If I'm starting with A1, that's the M equals 1 case, right? And the M equals 1 case gives me a 0 right there when I plug into that recurrence relation. That is a nice happy accident. That means that A3 is equal to 0. It also means that once I get that 0, the next one in line, A5, is equal to 0, and so forth. So in this case, all the odd terms are actually equal to 0. That's nice. That means that I only have to deal with the even terms of my series. So everything that you see up here at the top of the page, in this region, A4, A6, A8, and so forth, those are the ones that are left in my series. And now I see, well, I have that already done, right? So let's go down here to the bottom and let's see if we can put it all together. So it turns out here that my y of x, I started out with something of this form. And now here are all the even terms. So I wrote out all the even terms here. And remember, A1 is actually arbitrary. So with A1 arbitrary, A1 goes with x. All the other odd order terms are 0. So what I end up with here is kind of two pieces. I have the even terms, which starts with A0, and then everything else associated with the even terms, that's that. And then I have the odd term here. And notice that actually, does the A0, I think he can go in here for the case of x raised to the 0 power. Everything actually works out so that you actually get the same value there, even when k is equal to 0, right? Because I'm going to have a -1 down here. And a 0 factorial is 1. Hopefully everybody knows that. So that this is my final answer for my series representation of the solution to this particular ODE. And now this is the general solution, right? I have two unknown constants, A0 and A1. And now I want you to take a minute here and think about this. Let me stop sharing. Go back and look at, hopefully you've downloaded the file and are looking at it in front of you. Look at what you're seeing there. You're seeing a y of x, which has a series expression plus a constant times x. So those are the two linearly independent pieces. Those are like my y1 and my y2 that we were using before. Okay, so now I'm going to go back and make a couple of observations, and we're going to see if we can get this same thing. And I want to show you that it's actually equivalent to what you would see if you attack this problem a slightly different way. All right, so here we go again. Okay, Hermite's equation, take 2. But let's use what we know a little bit anyway. We learned that a constant times x is part of a general solution for Hermite's equation. So let's use that and let's attack this problem slightly differently. Same equation, Now just assume that I know that y1 of x equals x is a solution. You can plug that in to that equation right up there. I've done it for you right here, and you can show that it works. Okay, so x is one solution to that equation. Now that I have one solution, I have a second order equation there, an ODE, and I have one solution to it. I can always use reduction of order. One of my personal favorites, ROO here, ROO, to find a second linearly independent solution. And now let's go through that just a little bit. Here is our equation. And remember, go back to your textbook, to your earlier appendix sections. My P of X is now minus 2X. And then my e to the minus P of X looks like this thing right here. So that means that via reduction of order, this is my expression for a Y2, right? So this is my ROO formula. Go back and look it up in your textbook. And now let's see what that guy looks like. Well, that's an e to the x squared over x squared. An exponential, an e to the x squared. I can write down a series solution for that. Go back and check out your formula sheets. This is simply, I have written it down here. This whole thing is, this is my series expansion, my series representation for e to the x squared. Okay, you should be able to get that at this point in the course. Now, once I've done that substitution, I'm just going to plug and chug through some of those details. I'm going to rewrite that expression in a certain form, and look what happens to it. I get this 1 over 0 factorial. This is one of the few times where having a 0 in the denominator doesn't scare the bejesus out of me, because 0 factorial is 1. So it turns out that I've got a 1 over x squared, a 1, and then all these polynomial terms. Okay, I have to integrate that puppy. When I integrate it, it's actually not that hard. I integrate the 1 over x squared, I integrate the 1, I integrate here by, I'm a little fast and furious with my details, but I'm interchanging the order of integration and summation. Done it several times in class. And so once I do that, I can do those integrals for all those polynomials, and I come up with something that looks like this. And so let me just rewrite that a little bit. I've got this x out in front. Here you see I've got an x to the power of a 2m minus 1 that you see here. And then what have I kind of redone a little bit here? Well, I've really just, I've distributed that x, and so that goes into all of these individual terms. So I end up with a 1 plus an x squared, and then I have this x that I need to multiply into that summation. That's a legal move as well, as long as that series is convergent. And so once I put it all together, what I come up with is something that looks like this. Hopefully you're following along with your notes. I have a 1 plus an x squared plus all that summation stuff. It turns out that the x squared can actually be thought of as the m equals 1 case here. So it actually works out that it fits the formula as well. So here is a 1 plus a series expansion for y2. All right, so I'm just going to look a little bit further here. Let's summarize. Now that I've got a y2, now I recognize that, Well, my general solution via reduction of order is that. So I have a constant times x here, and then another arbitrary constant times this series looking thing. Now go back to page 2 and take a look at that, because as it turns out, you can actually think about rewriting C2 as minus A0, and what you're going to get is exactly the same thing as what we started with back on page 2, I guess, once we figured out what the series solution was, when we were just doing our standard power series method. So as it turns out, what I've shown you here is that we could do a power series expansion, or we could do reduction of order given, one solution, and get to exactly the same place. All right, take a quick look at that on your own. Hopefully you can see all of these teeny tiny little letters. I apologize, that's a little bit small. I hope you can read them when you print them out. Those are two different ways to show you how to solve one of these second order ODEs. So I will see you back in class on Wednesday. Thanks a lot for joining me, and I'll see you next time.